everyone. This lesson, we're continuing with projectile motion. So we're going to look at, instead of just horizontal projection, we're going to look at when you can have any initial velocity at the start, any angle. We're going to simplify it down to just being from the ground only for now, to continue with the idea of taking bite-sized pieces. And and then some challenge questions along the way here. So to start with, I'm going to look at horizontal projection. We're gonna be looking for what the initial velocity is, which is a little bit of a trick, right? In comparison to what a little trickier than what we looked at yesterday. We'll start with that, and then there's a challenge question that kind of, challenges you to kind of work your way through the same way this would. There's an opening question left in here from past days, whatever, past lessons. Past times I've taught the course. I just left it there as another example of everything all worked out. If you want to go through it, I'm going to start with this in this video though. So this is a Flash applet or whatever that used to work. They killed Flash a little while ago. I think on one of my computers I can make it work still, so I've left it in here with a program that allows me to run it, but the school computer doesn't let me do that. So, but I'll use the example anyways. It's all worked out. So basically, the question is, what speed does this motorcycle need to come in at in order to hit the target, right? In order to go with horizontal projected projectile motion, right? And land on the target rather than landing in here and getting eaten by the crocodiles. Really low quality animation of it. It was kind of funny, but if you don't hit the target, you get crocodiles go snappity snap around you. Anyways, so looking at this, we need to recognize what we have and what we don't have, right? So vertically, we have lots of stuff. We've got an initial velocity of 0. We've got acceleration, and we've got the displacement. So vertically, we have lots of information that we can use, right? So if you look at that, that means we've got this. We've got the vertical displacement, vertical acceleration, and the initial vertical velocity. We can find out anything we want. We can find out the final velocity, and we can find out the amount of time that it takes to land, right? So the time to take to land is going to be the most interesting, because then that same amount of time, of course, is the time during which the sideways velocity is happening, and you know how far you need to go, and so you're going to be able to get what the velocity needed is. So let's select what kind of an equation, which equation we need here. So we've got displacement. We've got acceleration, got the initial velocity, and we're looking for the time. So let's decide whether we go right at it and do this or not. If we're looking for the time here, can we get away with this one and have it not be a full-on quadratic we have to work hard to solve? Yeah, we can't, because this is 0, right? So it's going to work out just fine, right? We're going to have a nice 0 there, simplifying this down, and multiply out, calculate terms, divide both sides. So I'll do all the math stuff, and we get plus or minus delta t. And so, of course, 2 seconds into the future is the conclusion it takes. It's going to take 2 seconds to land. Right? Then after that, it's kind of easy, because you're like, okay, well, in that 2 seconds, it needs to travel 48 meters sideways, right? And so we know the time, and we know the displacement, and really it's just a uniform velocity question. It's really common for students to use a uniform acceleration question, which technically you could do, is you just have to get rid of, make sure there's no acceleration. So the acceleration value would be 0. And so really you just have velocity equals displacement over time in that type of equation there, right? Yeah, so it would be 24 meters per second, right? So the speed you need. So if we were to check this, the applet, you used to be able to just press play, set the speed, and press play and see it land there. We'll use our other simulation here and see how far something goes sideways if it's launched from 19.6 meters up at 24. Excuse me. So 24 meters per second, 19.6 meters up at an angle of 0, and start, launches and lands 48 meters over. Takes the 2 seconds to land, and so on, right? So you can see everything is working, right? So questions like this can seem a little bit trickier because they're not the traditional, give you the speed and the amount you're falling and just ask how far over and how long does it take and so on, right? So the challenge question that goes along with this kind of thing is this one here, where you have an airplane flying along, going to drop supplies. They're just going to undergo horizontal projection, right? Projectile motion going to the bottom. So they're just dropped with a sideways velocity. And you're given lots of information. You're given the velocity of the plane, given how far it needs to land. The question is how far before the target, right? How far before the target does the plane need to launch or drop the goods? And so it's not your traditional gave you the velocity and so on, right? So it makes it a little bit more challenging, but not too bad. So I'll make a folder for that one to be submitted into. All right. So the next level of projectile motion, launching from the ground to simplify things, but any direction possible now. Okay, of course. Otherwise, you're not going anywhere. So if we look at this situation, we've got 11 meters per second at 60 degrees. And this applet, the way it was set up, I'll probably pull up the applet afterwards if I can find it. So 11 times cos of 60 gives us that horizontal component, and 11 times sine of 60 gives us the vertical component of the velocities. And so you need to recognize that you have to analyze that, right? You can't just work with 11. You have to work with the 5.5 for the horizontal stuff and the 9.53 for the vertical stuff. Okay? Typical questions in a situation like this, like what are some things you'd wonder about? You launch it at 11 meters per second. Like clearly, like how high does it go? How long does it take to get there? How far does it land? And all sorts of things, right? So maximum height, when it gets there, how far over it lands, how long it takes to land, distance over that it lands, maximum height and how far over it was when it was at maximum height. These are all things we can figure out. And the velocity hits the ground width as well, just like when we did the horizontal projection stuff. Okay, so those are your kind of classic questions. We could even add in, an extra question and be like, also, when does it get to, when is it at 5 meters or something like that? Is it at height blank, right? Set in some number. And in which case, you picture this projectile motion that it's going to go through. We're looking for some height h, right? Picture how the math would actually give you two answers, right? So, or should give you two answers because it's in that at that height 2 times, right? It's on the way up and on the way down. That's a good one to add to the mix as well. So let's get at it here. Maximum height. So if you're looking at the initial velocity vertically like this, I think what I should start it with here, just to be more clear here, is we need to recognize that the vertical stuff is all that matters, right? So we've got v1y equals whatever the number was, 9.53, 9.53. And the acceleration in the vertical is the negative 9.8 due to gravity. And what else do we have for maximum height? That's the trick to realize, right? The other thing we know is that our final velocity in the y direction is 0. And that's the hidden information in something like this. So first of all, noticing that we're working with vertical stuff, vertical velocities and accelerations, and then noticing that final velocity that's kind of missing in at least in the question, right? So we look at this and we say, okay, well, we've got our delta V, right? The delta V is built in, has this idea of the final velocity of 0 built into it. So I didn't communicate this as well last time around, but this is V2 minus V1, which is the 9.53 take away 0. Okay, that's 0 from here. Okay. And multiply both sides by time, divide both sides by negative 9.8, end up with it taking 0.972 seconds to get to the top. Okay, so So that's it for now. I guess plus when is it at that height or whatever. But yeah, so we have that time. Then for the maximum height, we're going to need to find that delta dy, right? So we could look at the formula for the area and get it, or we could look at the formula from the equations. Okay, so either way, same results. It's just the area of the triangle. Knowing now that that base is 0.972, or we'd have the time variable in our equation for displacement. I suppose we could have looked at the equation for velocity and displacement directly. Would it be the v2 squared? vt squared equals v1 squared plus twice acceleration delta d. So we'd be able to say, okay, well, we could use that one too if we wanted, right? We have the final velocity of 0, the initial velocity of the 9.53. Let me just double check that. And twice the negative 9.8 delta d, right? So we should be able to calculate that one as well and see how that one goes. So we need 9.53, need the negative 18.6. I'll just show you here. 9.8 times 2 gives us that 19.6. Sorry, good thing I checked. So minus 19.6. Delta D equals 0. Take away the 9.53 from both sides. And get our negative 9.53 equals negative 19.6. Delta D, dividing both sides, just give us that same number there of the 4.56. Oh, I forgot to square. I was like, something's off here. I'm not getting the right number. So that needed to be squared. So that changes my numbers drastically. So hopefully at home watching this, you're thinking, wait a minute, what about the square? But if you weren't, then what I did for you there, not on purpose, but we could pretend it was, just watch for the kind of mistakes that can happen, right? So 90.8209. 90.8209. So whatever, 82. And now we're subtracting that from both sides. That hopefully gives us that same number of 4.63. I was looking ahead to that division. Wasn't going to give the right number. I was thinking, oh man, I have to try and fix this. All right. So negative 90.82 dividing both sides by negative 19.6. The moment you've all been waiting for. Coming up shortly here. Divide by 19.6 equals 4.63. Right? 4.63. It's just nice to see that it works. As long as you don't make mistakes along the way, of course, right? So 3 different ways that one is calculated for you. As long as you're choosing an equation and that has all the things in it you need, and you do the work correctly, you get the right answer, which is great. How far over? That's the maximum height, right? So max height is 4.63 meters. How far over is it when it gets there? This is where you have to recognize that this was all acceleration calculations. This just needs to be uniform velocity, right? And so for this one, we have to recognize that horizontally, how far over, talking about horizontal information, well, Vx equals, our number for that one, Vx is just 5.5 meters per second the whole time, right? So 5.5 meters per second, and we could add in constant velocity with an exclamation point, because that's often botched, if you will. Yeah, and so there's no acceleration to deal with at all. We know the time that it's traveling sideways for is 0.972. And so we can just get the displacement directly from the velocity displacement time equation, right? So you're not looking at the fancy sheet for this one. You're just using more basic knowledge. plug in the numbers. It's all out. Okay. So now we know over 5.4334 meters, and you're at a height of 4.63 after 0.972 seconds. All sorts of things we've managed to calculate. So how long do you land? Well, one way you could do this, of course, is just to say, well, it's going to be the same amount of time again, right? So one logic is just the same amount of time to go up as down. So 1.94 is your answer, right? I can show you another way as well, but that should be, we've justified that makes sense already. The other way would be to say your displacement's 0 and see what you get for that. While we're at it though here, just say, okay, we've got this like 1.9 or 1.94 seconds total. It's traveling sideways that whole time. And so that's, again, one of our just horizontal uniform velocity questions. So not uniform acceleration because it's 0, right? We have our 5.5 and our 1.94 in there. And so we solve out for the same reasons. We get that it lands 10.7 meters over. Okay. So we talked about how, the velocity, it ends up with back to the original height is the same as it was at the beginning. We can add that in as well if we wanted. It's all sorts of things we know. The driving principle behind it, though, that we've done in the past that confirms this. So, like, if we wanted to check this logic, these are some things that we know based on the idea of constant acceleration or uniform acceleration. But the one we know for sure that's just without any extra kind of intuition is that displacement ends up being 0, right? So it goes up, comes back down. So that's just 100%, like, there's nothing else that you can, no sort of fancier ideas needed. You end up back where you started, right? Well, you've got that, and you've got acceleration is negative 9.8. Negative 9.8. And meters per second squared, and your initial velocity in the y direction was the 9.53, if I remember right. Okay, so if you use an equation from the uniform acceleration stuff for that, we should be able to get everything else to do with it. You can get the time, and you can get the that was v1, so I need v2. Right, you can get the final velocity, and you can get the time. This was actually v1, of course. Starting velocity, right? So yeah, if you do that, you'd be able to get that same amount of time. Like this would lead to, you're probably going to want, I'm not going to do the whole thing right now, but you'd want to do this first so that you avoid the quadratic aspect of it, and then this number, get that one, and it's going to end up being 1.94. So that'd be a good practice thing for you to do. If you can't get 1.94 as an answer, then you need to ask for help. Okay. Final velocity. So intuition should be, of course, that we end up with that same velocity at the bottom as we started with. So basically, we should have 11 meters per second, right? And think of the angles, whatever, right? So to show that it's true, we're going to say, okay, well, we know we have the horizontal velocity still. The vertical velocity, we absolutely, in this process here, would have got negative 9.53 as an answer, right? And so if we were to look at the 5.5 and the 9.53, and you calculate out, the numbers and so on, notice that we really just have the same x and y components, right? And so as, if we did the Pythagorean theorem stuff, we'd find that we have the 11. And if we did the tan inverse of the angle, right? So angle here, theta is going to equal tan inverse of the 9.53 over the 5.5. And you know that it's going to be the same angle, whatever it was before, because you got the same components, right? So the angle was 60 degrees. So do tan inverse of 9.53 over 5.5, and you're going to get 60 degrees unless there was some rounding along the way. Let's see what happens here. 9.53 divided by 5.5. And we're going to do tan inverse, boom, and it gives us the 60 degrees, of course. Okay. So this applet here if it runs still. Yeah, this is another one of those flash ones that doesn't work anymore, but basically it launched, it landed, the distance over. Not one of those ones where we can, in the applet anyways, the way it worked was like, the to hit the target would be a different question, I guess, right? But we can go to this program and have the 11 and the 60 and see where it goes. I think we want that as 0 for now because we're doing the simple case. You launch it and see that it lands a distance of maximum height of 4.63, 1.94 seconds, horizontal distance of 10.7. Is that what we had recently? I don't know when we did that one earlier. It's long enough ago, I don't remember. I guess I never did that one yet. Oh yeah, we did have it, 10.7. Yeah. Anyways, so it confirms everything quite nicely for us. I've got a couple different applets that show this kind of thing, but I don't think you need to keep going through all of them. So another challenge question that it's not going to be assigned right now, but think about like what speed would you need to hit the target then in this situation. Okay, so this isn't a submit in a Dropbox kind of challenge question. This is just for yourself, okay? Just to see if would you be able to figure that out? Okay. So the questions here, I just want you to skip number 4 if you want. There's optional extra practice there. But if you look through here, this one's really quick and easy because it's just based on an understanding, right? What's the ball's horizontal and vertical accelerations at these key spots? Those are quick and easy, just knowledge answers. And then this is the classic, give you the velocity and the direction and ask you all the things about it. Some of these are a little less complete, right? Where it gives you the launch speed and the angle, and then it's just asking a couple things, and so on. So 3 is actually kind of very similar to 2 as well. If you were looking at skipping a little bit to save time, do 1 and either 2 or 3 kind of thing. 4 I already stated is optional practice. 5, I think you'll find is kind of like the tennis ball going over the net question. Little tricky, little tricks there to do with figuring that out. Then what's the initial velocity? So a different style question, number 6. So I wouldn't skip number 6 and number 5, right? Because otherwise you won't see that kind of stuff. And if it shows up on a test, you're going to have a not great day. So anyways, we want you to have great days. So there we go. All right. That is it for me. Signing off. See you later. Thanks for watching.